Hi everybody, this is Mr. Wells, and I just wanted to go over the first problem on here since we didn't have a chance to do it in class today. So hopefully this will give you a good idea of what we're looking to accomplish here. So we have this worksheet, and I've written the equations for acceleration up there. So we have this car, and they want us to make a well-labeled diagram of the situation. The diagram is not essential. You don't have to do that in every problem. If it helps you, go for it. If not, don't worry about it. But here we have a velocity equal to 0, and that would be VI. And later this car is over here, and it's moving. It has a velocity VF equal to 20 meters per second. And the change in time here, the time it took to do that, delta t is equal to, that's 28 meters per second. So that's 20 seconds. Okay. So make a well-labeled graphical representation of the situation. I'll do the graph later. And we want to list the given quantities and so on. So we always want to do this list. So I'm going to split this, since this has two parts. They actually have two questions here they want us to solve. I'm going to break this into two parts, and the first one I'll have VF, VI. We always want to list our variables. VF, VI, acceleration, change in time, and our change in position. Since we're horizontal here, I'm going to use X. Okay, you can use Y, delta Y, if it's a falling body problem. Okay. Then we're going to look at this, and we're going to say the car accelerates from rest. So that tells us that our initial velocity is equal to 0, and it gets to a speed of 28 meters per second. So that's also a velocity, so that'll be our final velocity. And it does that in 20 seconds. So that's the time interval, 20 seconds. And they want us to find, in part 1 here, they want us to find the average acceleration. So we are looking for acceleration, and we don't worry about that. So we look up at our equations, and we can see the first one's going to work here. So VF is equal to VI plus the acceleration times the change in time. And those, if you look at that, we always want to write it out in terms of the symbols first, because then it's really clear how to substitute in. So I'm going to say 28 is equal to 0 plus A times 20. And if I'm solving for the acceleration, I'm going to divide both sides by 20. So that's going to be 28, and that's the velocity, so that would be meters per second. And I'm dividing by a time of 20 seconds. So I did this previously. That turns out to be 1.4, and then meters per second per second. The other question they ask us to do is how far does it travel? So we've got the same list of variables. So final velocity of 28, meters per second. We've got an initial velocity equal to 0. We now know the acceleration is 1.4 meters per second. I know that delta t is equal to 20 seconds. And finally, we know we are looking for the change in position, which is how far it travels, delta x. So I can use any one of my equations that we want, because that has delta x in it anyway. I'm going to go ahead and use the second one, just because we don't get to use that very often. So just to see that that's useful on occasion. So delta x is equal to 1/2 times the final velocity plus the initial velocity times delta t. So delta x is equal to 1/2. Final velocity is 28. The initial velocity is 0. And multiply that by the time, which is 20. And And from that you get 280, and the units would be meters. Now the graph, it's nice to look at the graph just to get a little practice with the graphing and see how it works out. So you got to pick a scale, and I did this beforehand, so I'm going to say that's 4, 8, 12, 16, and 20. 0, and on the other axis I'm going to go up by 4s. So that's 4, 8, 12, 16, and let me change colors here so it's a little easier to see. 16, and that is 24. And so we can plot points on here. The velocity at time equals 0, that's our initial velocity, is 0. At time equals 20, the velocity is 28, which would actually be right up here if you look at that. And so if we graph this, we've got that. And now how does this relate to the two problems? Well, in the first one, you can see we end up taking the change in velocity over the change in time, or calculating the slope. So we know that the acceleration is equal to the slope, and we know that the displacement is equal to the area. So delta x is equal to the area. So if you do a little math, the area would be 1/2 the base, which is 20, times the height, which is 28, which is really what we did there. So you can see that the graph is related to the numbers. So that's number one. So you should be able to go on and continue with the rest. Do as much as you can. Like I said, the picture is not essential, so I'm okay if you skip that. But the rest of it you should be able to do, and I'd like to go over that on Monday. Alright, that's all you need to know.